Let us continue with example 2. Say we are interested in determining the resistance of resistor RB if our voltmeter is measuring a 5 volt potential. In our circuit below, we have a 4 amp source that is feeding current to RB, and it's also connected to another 4 amp source. At the top of our circuit, between RA and RB, we have a resistor RC. To employ NVA, we will follow our 4 steps. The first step is to assign nodes of our system and leg currents to all branches and elements. Within our system, we have 3 nodes, A, B, and C. Node A connects our left-hand side 4 amp source to RA and RC. Node B connects RC, RB, and our other 4 amp source. And node C connects our 4 amp source, RA, RB, and our 4 amp source. We note that our voltage at node B is going to be equal to 5 volts, i.e. VB is equal to 5 volts. Now we assign branch currents as best we can. We assume I1 runs from node C to node A through RA. We assume I2 runs through RC between nodes A and B. And we assume I3 runs between nodes B and C through RB. Step 2 is to assign voltage potentials across our resistors consistent with our passive sign convention, such that VA exists across RA as designated by the direction of I1, VC exists across RC as indicated by the direction of I2, and VB exists across RB as indicated by the direction of I3. Our third step is to construct n-1 KCL equations. We have 3 nodes, thus we need 2 KCL equations, and if we apply these at our non-zero nodes, we will construct KCL equations at A and B. Simplifying our circuit by removing our voltmeter and recalling VB is equal to 5 volts, we can begin to construct our KCL equations. Looking at node A, we have 4 amps exiting, I1 entering, and I2 exiting. That is, I1 is equal to I2 plus 4 amps. Our KCL equation at node B has 4 amps entering, I2 entering, and I3 exiting. That is, I2 plus 4 amps is equal to I3. Our fourth step within our procedure is to apply Ohm's law in terms of node voltages. Starting with our KCL equation at node A, I1 is equal to VC less VA per RA, where VC is equal to 0, i.e. we designate that as our ground. And this is equal to I2, which is expressed as VA minus VB over RC, plus 4 amps. We can directly solve for VA given RA is equal to 10 ohms and RC is equal to 5 ohms, such that VA is equal to minus 10 volts. Expressing our KCL equation at node B in terms of our node voltages, I2 is equal to VA minus VB per RC, where we recall VB is equal to 5 volts as measured by the voltmeter, plus 4 amps is equal to I3, which is expressed as VB minus VC per RB. Recalling VB is equal to 5 volts and VA is equal to minus 10 volts, given that RC is equal to 5 ohms, we can therefore solve for RB. RB is found to be 5 ohms.